And now you look at this example here. For this example, we don't have the real part. And you can see from our calculations, the real part, the exponential, this number are coming from where? Are coming from here, right? So if we don't have this number, if we don't have the real parts here, if the location of the poles is on the imaginary part, basically is the real part is 0, then basically saying that exponential is, then there's no exponential profile. So accordingly, our curve, without any exponential curve, then oscillation will be just keep going on its own. Okay, so hopefully you know what I'm saying here. Again, this one you have to practice. You have to your own practice. Do you need me to help you on the practice? Yes or no? How do you think? Give you 5 seconds to think. If yes, raise your hand. 5, 4, 1. If you need my
you
help,
just go 5, 4, 1. You just totally skipped us for 2 seconds.
if you need my help, raise your hand.
For what do you? How are you going to help us?
Like,
I want your answer before I tell you how can I help you. No one. Okay, you guys so smart.
no.
My way to help you to make another homework.
Oh no, I'm good.
Make another homework.
No, I'm
Just
good.
force you to do all the kind of calculation and plotting.
No, I'm good.
How about an optional one? that
Then
we can
if then
maybe-
the other optional one is put onto the test. Okay, so I've done this one for many times. I think it should be your turn. Otherwise, I won't be able to make the good numbers and quickly help myself. I don't have the calculators with me. I can pick up the easy numbers. I mean, the fit into my homework, right? Oh my goodness. But anyhow, that is the whole thing. You have to practice a little bit.
What you should do is, get our names, put it in a hat, and then draw one, and then have us do it on the board.
Or not.
No, that is yeah, we are not.
Sarah, shut up.
Yeah, we are not middle school. Okay. So now for this case, and for this system, the transfer function like this. So again, this one fit into our first case. For the first case, then A simply has the opposite sign. So which means the A becomes a positive number here. So that kind of exponentially growing, and which means for this kind of control system, we call it unstable. Unstable, that means the response, for example, you imagine the X will be the degree of freedom. The degree of freedom basically leaving away from the equilibrium position. That meaning the system is unstable. Okay, like this.
When would you want that type of response?
When we want an unstable response.
Yeah.
Because like F-16, the flight jet, they want to be agile. So they want to be unstable to the certain period of time or certain moment and then coming back to the stable status. And when they have to strive for away from the threatening, say if they want to change the status away from missile attack something, then they have to change very quickly. And only the system is unstable, then make that happen. If the system is so stable, like elephant, then you die. You just be the target. Oh, they are so slow. Right? Okay. So, all the new, I can tell you, if you have interest, our new flight jet and even B-2 bomber. Let me try to draw this shape, something like this one, right?
What is this?
B2.
Bombers, B-2 bombers. Those shape in nature is unstable. If they lose the power, they will right away to going down. There's no way to. This system by nature, by design, is unstable. Okay, if you have interest, you can look for the information, but I don't think you can find much. Okay, but this system in aerodynamics is unstable system. So basically, this kind of system, why they're so expensive, at least in the control system, they have very fancy, very good one to make things happen. Okay, so. So another one is here the similar way. If we have the previous example is we don't have imaginary part, so the system won't oscillate. And here, in addition, we have the imaginary part. So the system not only exploring, but also we're oscillating. Okay, so hopefully you can get certain feeling about the system here. And if we have another pulse here, then the system will be 0, then the system will decay. So this page is a good one. Basically, this one gives you the very complete summaries of the dynamic systems, and this one will be good for you to pick up the vibrations, and also will be good for you to pick up the controls. And in terms of controls, in our purpose, we try to stabilize. We try to design a stable system, so which means the two categories are what we're going to pursue in ME409. And we might talk about this one, it's called a marginal stable system. For the two, that are the purposes, and we call it unstable. And usually in control systems, we try to avoid the two response. Okay. So this is the content, and again, that is in C2, 4, and a few pages down the bottom here, you should be able to get it. And that's it. Any? Okay, I said that I want to provide you some
homework
of
hints.
the homework. So for the first question, basically has been going over very much. So here, for this system, for the system like this, s squared plus 4s plus 8, we have poles here. And for the systems like this, then I'm asking you what is the content of, what is the response of xt, then basically here, the black one corresponding is this response, right? And this one is corresponding to this response. So using this analogy, you should be able to quickly answer these questions, right? So here you simply change the contents here, or if you like, say this system, characteristic equation for this system, characteristic equation for this system is s plus 2 squared plus 2 squared equal to 0, right? So for this system, the characteristic equations for this one would be s plus 5 squared plus 2 squared equal to 0, right? So once you have a characteristic equation, you can backwards. So which means the GS will be equal to s squared s plus 5 squared plus 2 squared, right? So in this way, under the unit impulse response, you simply calculate inverse of G as you can obtain the output, right? So kind of the backward, and this design, for this question, I simply want you to recognize how can you observe the location of the dominant poles and to guess, to rebuild the system dynamics using this way. Okay, so basically the last one is kind of reverse the whole things from back to the original. So hopefully you can get this kind of the problem here. And this one is pretty straightforward. The second one is you simply, I would say, using whatever method to derive the transfer function, the relation between output P over R. And then you calculate the transfer functions and they draw the corresponding signal flow graph. The signal flow graph is here. You can put the label. Here is the variable called V1. Here is a variable called V2. Here is a variable called QS. Here is a variable called P. And here another variable called RS. So for this, the first one to build up the signal flow graph is to label the variables here. Okay, so here is PS, and here is Q, and here is V2, here is V1, and here is R. Okay, and then you simply build up the path. And for example, for Q here, between V2 and Q here is the forward. You follow this arrow, so the path is here is 0.6 over S. The path gain is like this. Okay. So for example, from P, we have the feedback path to R here. So V1 will be equal to, from here you can see V1 is this plus is 1 here, that is from R, and here is minus. So minus we'll put into here. So that is the feedback from here. You have the feedback forward here, and we put a minus here. Something like this. So once we have this one, I think the remaining should be very straightforward. Okay, so that's the procedure. And again, you see what I did is sometimes we won't provide this kind of variable. You can define your own symbols there. Okay, locate those nodes and then define the path. And this one should be very straightforward. This one, you simply do the calculation, apply Mason's rule. And then I can tell you the answer is no. But I want to see why they are different. So I want to see your deliberations. For the fourth questions, again, for this one, this is our output. And this one, we have two inputs. This one and this one. And again, you simply backwards, for example, here C will be equal to G3 multiplied with this one. Let me call G3 is, say, let me make up any number, say X1, okay? So X1 will be equal to G2. This is X1, okay? So X1 will be equal to G2 times this one. This one will be coming from DX, and D is our input, and plus G1, and times this one. Oh my goodness. So here, let me put X2 here. So G1 multiplied with X2, and minus this one here, right? That minus this one. This one is H1 times this one times X1. Okay, we're good. And then we go to X2. So X2 will be equal to GC times R minus the H2 times C. So you simply plug in this kind of tier-wise calculation, just do it. And here R is another input. So here for this example here is called the multiple input single output. And I believe in your final representation you will get the CS equal to a certain something times ES plus certain something and times R over S. So therefore, let me call this is say the GT1. Okay, let me call the GT1S. They call the GT2S. So therefore, the answer C over D will be equal to simply is GT1 over S. And C over R simply is GT2 over S. Okay? This one is a little bit more straightforward. This one you have to do certain calculations. So determine the transfer function. Right now I give you the numbers, and determine the poles and zeros. So for this case, if the numerator, I can tell you numerator is only constant. So given a constant, there's a no zero, right? So you simply answer is no. And the poles, then likely you have to use your calculators to solve for the roots of whatever the polynomial equation in the denominators. And then determine the YT. So this one will take a little bit time. Basically, you simplify the transfer function, then you repeat your exercise in homework 1, doing careful the plus inverse calculations. Okay. And once you have a number, you put into the blackboard to verify your calculation before you determine this one. And the steady state value, then we talked about this one before, and you can calculate this. Okay, so this one should be very straightforward.
In the earlier question 4, if we were to change it into a signal flow graph, and then we wanted to look at like the forward path, and the C over D, the transfer function for that, would you start at the D and find the forward path from there?
Yes, you mean the previous one, right?
Yes. Would you start at the disturbance and do the forward path from D, or would you?
Yes. Okay. So in this way, you should have the Q path Q. In this way, you should look for this Q input. So which means Q input entries.
And so 2 4.
Yeah, Q. Yeah.
Okay.
And the Q path basically will share the network. Will share the same network.
Okay.
And it's the way. Okay. So these are only 5 questions. I thought we had 7 questions. Probably I forgot the other 2. Then I will revise the content. No. No. Okay. Okay, that's pretty much. And again, these questions will be a little bit tedious and verified with the Blackboard answers. Okay. Okay. Thank you.